Hello students, welcome to ALPHORES e-learning channel. This is K. Nageshwara, your physics faculty. Today we are about to deal with session number 97, current electricity, second year Neet. See, in the last session we have discussed about meter bridge, and what was our conclusion? If you take a meter bridge and under balancing condition, P by Q is expressed as L1 by 100 minus L1, where L1 is balancing length. Okay, and P is resistance kept in the left gap, Q is resistance kept in the right gap, or you can take it as Y by X, whatever it is. Okay, so this is what our conclusion was, isn't it? And we have seen one or two problems based on this one also, isn't it? So today let us try two more problems. Okay, let us see what we can do with this. Let us try to solve these two problems. The first one is the resistance in the two arms of the meter bridge are 5 ohm and R ohm respectively. When the resistance R is shunted with an equal resistance, the new balance point is at 1.6 L1. The resistance R is. So here the circuit diagram is given like this. 5 ohm resistance is connected in the left gap and the R ohms resistance is connected in right gap. Okay, so in these two gaps, two resistances were connected. What was said? A resistance in the two arms of the meter bridge are 5 ohm and R ohm respectively. The resistances in the two arms are 5 ohm, R ohm respectively. At that time, what is the balancing length? L1 is the balancing length. Corresponding to this situation, okay, what you can write? You can write 5 by R is equal to L1 by 100 minus L1. Okay, when the bridge is balanced, this is what, ratio between these two resistances. If you imagine here P, if you imagine here Q, P by Q is equal to L1 by 100 minus L1. So in place of P, what we have 5. In place of Q, we have R. So 5 by R is equal to L1 by 100 minus L1. Right. Let us take this as equation number 1. When the resistance R is shunted with an equal resistance, so this R is shunted. Shunting in the sense, if any resistance is connected parallel to some other resistance, we say that the resistance is shunted. We say that this R is shunted if another resistance is connected parallel to this one. And it was said that in the question, when the resistance R is shunted with an equal resistance. So with what resistance it is shunted? With a resistance equal to R ohms only. Okay, shunting in the sense connecting a resistance parallel to the given resistance. Then the given resistance is said to be shunted. Okay, so in this situation, what was the balancing length? 1.6 times L1. Earlier it was L1, now it is 1.6 times L1. So corresponding to this situation, let us write the balancing equation. If let us say somewhere here the balancing length might have been obtained. Okay, so how much is this length? This length is equal to 1.6 L1. So let us write. So here in the left gap, what do we have? 5 only. It was not changed. In the right gap, what is the effective resistance? If two resistors are parallelly connected, effective resistance will be taken as R1 R2 by R1 plus R2. So if that is the case here, R1 is R and R2 is also R only. So R into R by R plus R. So what you will have? R square by 2R. R gets cancelled. So R by 2 is effective resistance of this parallel combination. So R by 2 is the value. So what you can write here? R by 2. So 5 divided by this resistance is equal to, what is the new balancing length? 1.6 L1 divided by the remaining length will be what? 100 minus 1.6 L1. Let us take it as equation number 2. Okay. Now let us divide equation 1 with 2. What do we have? 5 gets cancelled, R gets cancelled, and then you will have 1 by 2 here is equal to L1 gets cancelled. So you will have 100 minus 1.6 L1 by 100 minus L1 into 1.6. So this is what you are left with. Okay. Now let us simplify this. If we simplify this, what do we get? 1.6 divided by 2 will be 0.8. Isn't it? 0.8 multiplied with this one, what you will get? 80 minus 0.8 L1 is equal to 100 minus 1.6 L1. See, ultimately what is our goal? We have to find out resistance value R. What is that R value is? So for that, we need to find out what this L1 is. So once you know what L1 is, later you can substitute here and you can find out R. So let us try to find out L1. So 80 minus 0.8 L1 is equal to 100 minus 1.6 L1. So if it is shuffled, what you will have? 0.8 L1 is equal to 100 minus 80, it's 20. So therefore L1 is equal to 200 by 8, it's 25 centimeters. So what is the value of L1? 25 centimeters. So let us replace it here. Therefore from equation 1, 5 by R is equal to, in place of L1 what I am going to replace with? 25. Okay. So 25 divided by 100 minus 25, 75. So what you will have? 1 by 3. So R is equal to 15 ohm. So this is the answer. Okay. So that is how you can solve this. Now see the second question. When two unknown resistances X and Y are connected in the left and right gaps of a meter bridge, the balancing length is 70 centimeters. So when X and Y are connected, balancing length is 70. It means X by Y is equal to 70 by 100 minus 70, isn't it? That's what you can write equation for balancing situation. So when a 5 ohm resistance is connected in parallel to X, so now what was done? To X, a 5 ohm resistance is connected. Then the balancing length becomes 35 centimeters. So the values of X and Y are respectively. So we have to find out values of X and Y. So let me draw one small diagram here. Let us say this is resistance in the left gap. Okay, so this is the meter bridge. That's how we'll imagine picture. So A, B. Okay, so this is X and this is Y. So initially what was the balancing length? 70 centimeters. Maybe somewhere here the balancing length was obtained. So corresponding to this situation, what is the equation? X by Y, like P by Q is equal to L1 by 100 minus L1. So balancing length, how much was the balancing length? 70 centimeters. So 70 by 100 minus 70, it's 30. So what you will have? 7 by 3. Let us take it as equation number 1. Now what was done? When a 5 ohm resistance is connected in parallel to X, so through this X, a 5 ohm resistance is connected in parallel. Okay, then what was the balancing length? 35 centimeters. This Y, it is intact. It was, to this Y any other resistance was not connected. So only to this X resistance, X ohms resistance, 5 ohm resistor is connected in parallel. Okay, so now in this case balancing length was 35 centimeters. Maybe somewhere here the balancing length was obtained in the second case, 35 centimeters. So let us write equation for that. What is the effective resistance here? 5x by 5 plus x, R1 R2 by R1 plus R2. R1 is 5, R2 is x. So R1 into R2, 5 into x by 5 plus x divided by y is same. It was not disturbed, is equal to, what is the balancing length? 35 centimeters. So L1 is 35, 100 minus L1, 100 minus 35, it's 65. So what you will have? 7 by 13. Okay, so now let us simplify this one. What you will get? If you simplify this, 5x by 5 plus x into y is equal to 7 by 13. Let us take it as equation number 2. Now from this equation I can write what x is. X can be written as 7y by 3. Now let us substitute here. Let us replace x with 7y by 3. What you will get if x is replaced with 7y by 3? Or we can do one thing. We can divide these two equations. If these two equations are divided, 1 with the 2, what happens? X by y gets cancelled, right? Dividing 1 with the 2. So we will have x by y gets cancelled. So here what you are left with? 5 plus x by 5, isn't it? Is equal to, here 7 by 3 is there, into 13 by 7. 7 gets cancelled, isn't it? So if that is the situation, let us simplify further, so that we will be able to get the x value. So what you will have here, 3 5s are 15 plus 3x is equal to 65. So 3x is equal to 50. That implies x is equal to 50 by 3 ohms. So what is the value of x? X is equal to 50 by 3 ohms. From this equation, what is y? Y is equal to 3x by 7. 3 by 7 into, just now we have obtained x value, 50 by 3. 3 gets cancelled. So 50 by 7 ohms. So this is the y value and this is x value. So that's how you can solve the problems related to Wheatstone's bridge application, meter bridge. Okay. Let us proceed with one more topic. It's a potentiometer. Potentiometer is another application here. Here also we talk about balancing point, balancing length, all these words are used. Okay, so let us talk about potentiometer. So now let us discuss about potentiometer. Potentiometer. Before I start what this potentiometer and what's the theory behind this potentiometer or based on what principle it works, let us try to understand few other points connected with this potentiometer. I'll take a circuit here. Let us say two resistors were connected like this. There is a battery. Let us say one key is there, so key is closed. Let us say the battery supplies a potential equal to some V potential. Let resistance of this one is R1, resistance of this one is R2. If I ask you to find out potential drop across this first resistance, what you can do, theoretically you can write potential drop across the first resistance as, since a current I is passing through that one, according to Ohm's law, V1 is equal to IR1. So that's how we'll be finding potential drop across R1. Okay, but if you wanted to find the potential drop across R1 using any device, there is one device that can be used. It's voltmeter. Basically, we very frequently we see three kinds of meters: galvanometer, voltmeter, ammeter. Galvanometer is used for detecting presence of current. Whether the current is there or not, we can identify with the help of galvanometer. We cannot measure. But by making slight modification in the galvanometer, we can make a device called ammeter. Using that ammeter, we can measure the current. And to measure the potential drop across these resistances or across any circuitry element, we can use another device called voltmeter. What is that? Voltmeter. So, if I wanted to measure the potential difference across this R1, a voltmeter will be connected like this across this resistance. So, this is what? Voltmeter. Now, the voltmeter shows some reading. Remember children, voltmeter will be always connected across the circuit element because you are finding the potential difference across the resistance. It means you have to connect at this point, across. You have to connect across. Okay, so when you connect the voltmeter across, automatically it becomes parallel to the given circuit element. So voltmeter is always connected parallel to the given circuit element. So here when you connect this voltmeter to, across this R1, it shows some reading. Okay, how much reading you expect out of that voltmeter? You expect this reading V1, but you won't get that reading. Whatever theoretical value you are obtaining here, V1 is equal to IR1, that value won't be seen here in this voltmeter. There is a reason for that. If this voltmeter is not there, I value of current is passing through this R1. If voltmeter is connected here, what happens? Some of the current passes through the voltmeter also. Now, current which is passing through R1 is not equal to I. It will be slightly less than I. If that is the situation, whatever reading voltmeter shows, that reading will be different from this reading. It means, usually in the laboratories, whatever voltmeters we use for measuring potential drop across any given circuitry element, that potential drop shown by the voltmeters is not accurate, not correct value. Slightly it will be different from true value. There will be some error shown by the voltmeter. All this is happening because voltmeter is drawing current. Okay, let us say I1 is entering here and here I minus I1 will enter. Okay, so this voltmeter is drawing some current. Because of that only this problem is arising. Because of that only whatever reading is shown by the voltmeter is not accurate. Okay, so what to do? What is the solution for this one? Okay, to overcome this one. If you wanted to find out potential drop across any circuit element accurately, what is the solution? The solution is this one. You can use potentiometer. Potentiometer is something that doesn't draw current from the main circuit. To whatever circuit you connect this potentiometer, from that circuit, potentiometer, it doesn't draw any current. It is a self-driven device. It will have its own cell for its operation. Here, voltmeter, it doesn't have any of its own source. Okay, it is drawing current from the main circuit to whatever circuit it is connected. But whereas potentiometer, it doesn't draw the current from the circuit. So that's why whatever reading potentiometer shows, that reading is the absolute potential difference across the given circuit element, or across a cell. If you connect a potentiometer, it shows absolute EMF of the cell. So these are the this is the advantage of potentiometer. Of course, potentiometer will also can also be used for some other purposes. We will discuss about those things. The main important point that you should recollect when you remember this potentiometer is a device which can be used to measure potential difference accurately. Absolute potential difference can be identified. Okay, so based on what principle it works, let us try to understand that point. Potentiometer principle. Potentiometer principle. Let me write the statement here. It states that when a constant current is passing through a wire of uniform cross section, then potential drop across any portion of the wire is directly proportional to its length. Whose length? That portion's length. Okay, if you consider a wire, okay, if you wanted to find out potential drop across any portion of the wire, that potential drop will be directly proportional to length of that portion. So that's what the principle is. And if you observe this principle very carefully, in the principle two important conditions were mentioned. Unless or otherwise you fulfill those conditions, you cannot realize this principle practically. So what are those conditions? The wire should be of uniform cross section. This is one important condition. The other condition is the current should not fluctuate, it should be constant. So when these two conditions are fulfilled, you can realize this potentiometer principle. So remember children, the potentiometer principle is when a constant current is passing through a wire of uniform cross section, potential drop across any portion of the wire is directly proportional to length of that portion. Okay, so based on this principle, we will be able to develop the theory related to potentiometer. So let us develop the theory related to potentiometer. Now let us deal with the theory of potentiometer. This is how a potentiometer circuit looks like. Whatever this primary circuit is there, that's called potentiometer actually. This is called secondary circuit. If at all, if you wanted to find out internal resistance, if at all, if you wanted to find out EMF across a cell, if you wanted to find out resistance, potential drop across a given resistance, all those things will be connected here. So that part is called as secondary circuit, and this this is called as primary circuit, which is mainly nothing but potentiometer. So this is what your potentiometer should look like. Okay, so what are there? One cell is there with EMF E, and its internal resistance is written here, small r, and a series resistance Rs is connected, and there is a wire between these 2 points A and B. That's called potentiometer wire. Potentiometer wire. Okay. And here, unlike in the case of meter bridge, here there are no any restrictions. So the length of the potentiometer wire can be anything, 2 meters, 3 meters, 4 meters. Whereas in case of meter bridge, you are restricted to use only 1 meter length of the wire, 100 centimeter length of the wire. But here, this wire between A and B can be 2 meters, 3 meters, 4 meters, whatever length, according to the requirement. According to our requirement, according to whatever experiment we are doing, the length can be changed. Okay. So for time being, forget about this secondary circuit. This is what. For example, if you wanted to find out potential drop across a resistor in a circuit, that circuit will be joined here. Okay, so that is called as secondary circuit, and this primary circuit is what? Our potentiometer. Okay, so let me define few things. Let length of potentiometer wire is equal to capital L. What is the length? Capital L. Here I have shown in the picture that I value of current is flowing. If you wanted to find out how much is that current, how it can be expressed. Current I is equal to total EMF E divided by total resistance, isn't it? E equivalent by what? Effective resistance. Here effective resistance in the sense small r and Rs both are in series, And potentiometer wire also offers some resistance, isn't it? I will assume that resistance as capital R. So if a resistance of capital R is contributed by AB wire, and already in series with this potentiometer wire, RS is there and R is there. So all are in series only. So effective resistance will be equal to R plus RS plus resistance of the potentiometer wire. So what is this R? Resistance of potentiometer wire. Potentiometer wire. Okay, so this is what I value is. Let us take it as equation number 1. And what about potential? I will consider a small length L1, sorry L, because we will not be having a L1, L2 kind of things. Okay, I will consider a small length L. Okay, what about potential across this L length of wire? How it can be written? Potential across L length of the wire is equal to current passing through L length of the wire into resistance of L length of wire, isn't it? V is equal to IR. My interest is I wanted to find out potential drop across this length L, small l. Total length of the potentiometer wire is capital L. I wanted to find out potential drop across this small length L. So how it can be calculated? V is equal to current multiplied with resistance of this length of wire, small L length of wire. So how to find out what small L length of wire's resistance? It can be calculated easily. Total AB length of the wire's resistance is how much? Capital R. So over a length equal to capital L, resistance is capital R. So resistance per unit length is this one, right? So for over a length of small l, what will be the resistance? R by L into small l. So that's how you can write expression for the resistance. Okay, resistance of L length of wire, small l length of wire. So let us try to simplify this one. Further, how it can be written? V by L is equal to I into R by L. If you observe this one very carefully, whatever this I is there, in the potentiometer principle it was clearly mentioned that I is supposed to be constant, isn't it? When a constant current is passing through a wire of uniform cross section, potential drop across any portion of the wire is directly proportional to length of that portion. That's what we have written, right? So this I is constant here. Capital R is what? Resistance of the given potentiometer wire. That is also constant as long as the uniform cross section area of the wire remains intact. If it is uniform, this capital R also remains constant, and length of the potentiometer wire, that is also constant. So this overall, this I into R by L is what? It's a constant. So what you can say? V is directly proportional to small l. Can you say like that? So this is where actually we see potentiometer principle. Okay, so let us try to modify this equation. I will write this V by L as x equal to I into R by L. What is this x? V by L. Potential per unit length. Potential per unit length, or you can write it as how it can be written? Potential gradient. Potential gradient. Potential gradient. Remember, children? So this x is what? V by L, which is nothing but potential gradient. Okay, let us try to understand few more details connected with these equations. Already we know what I is from equation 1. What is I? E by R plus RS plus R. Okay, so let me take this as equation number 2. From 1 and 2, what I can write? I can write potential gradient as E by R plus RS plus R into R by L. So this is one important equation here. Let us take it as equation number 3. Now let me pick up this equation number 2. From equation 2, this potential gradient x can also be written as I into rho by A, where rho is what? Resistivity. resistivity. We have already discussed about this thing. Usually, the resistance is written as a rho into L by A, isn't it? Resistance is equal to resistivity multiplied with length divided by area. So from here, what is R by L? R by L is equal to rho by A. So that's what here R by L is replaced with rho by A. So then what did you get? What did we get? Potential gradient is equal to I into rho by A. This can be further modified as I into rho by pi r square. So these are all possible relations of potential gradient with various other parameters. So potential gradient can be expressed like this. It can be expressed like this. It can be expressed like this. It can be expressed like this. For example, if you are taking potentiometer wire as a combination of two wires, let us say one wire is of length equal to L1 whose resistance is R1, the other wire's length is L2 whose resistance is R2. In fact, you can take potentiometer wire as a combination of two wires also. Okay, so if you have taken like that, what you can do, look at this equation. When you have taken combination of wires, in the form of series combination, current passing through these two wires will be same, isn't it? So if you wanted to use this equation for this situation, I is constant in this wire and in this wire I is same. Therefore, what you can write, x1 potential gradient corresponding to this wire can be written as what? I into R1 by L1. Potential gradient corresponding to this wire can be written as x2 is equal to I into R2 by L2, isn't it? And if you are supposed to find out the ratio between potential gradients of both the wires, how it can be written? X1 by X2, II gets cancelled, R1 by R2 into, how it can be written? L2 by L1. So these are few important conclusions connected with the theory of a potentiometer. And look at this potential gradient relation with these things. It is dependent on what parameters? EMF, resistance of the wire, length of the wire, on all these parameters it is dependent, isn't it? So you can understand on what factors the potential gradient depends with the help of these equations. For example, if you have considered an ideal cell in the primary circuit, what is this? This is an ideal cell. For an ideal cell, remember children, it was already told to you, for an ideal cell, internal resistance is 0. Internal resistance is 0. Let RS is also 0. Let us say in the circuit, this series resistance. What is this? This is series resistance. These words are used in the numerical problems, you have to remember. So let us say series resistance is not connected. If that is the situation, look at this equation, how this potential gradient equation gets modified. X is equal to, small r is 0 because we have taken ideal cell, and RS is 0. So what you will have? E by capital R into R by L. So RR gets cancelled. This is equal to E by L. It means when you have considered ideal cell, and if series resistance is 0, this potential gradient is dependent on what? EMF of the cell in the primary circuit and length of the potentiometer wire. So like that, depending upon whatever situation he is describing in the question, you can clearly identify on what factors potential gradient depends. Okay, these are all the equations connected with potential gradient. Okay, so that's it for now. In the next session, we will continue with a few problems connected with this theory of potentiometer. Thank you, students.